Hello, and welcome back to part 2 of our lecture from chapter 6. In this part of the lecture, we'll talk about the dynamics of circular motion. Hello there. So we've got a tennis ball on a string, and I can demonstrate two types of circular motion here. If I spin the ball around in a horizontal circle like this, we've got uniform circular motion. And another way I can do it is to spin the ball in a vertical circle like this. Another example of uniform circular motion. In all cases here, the ball is going at approximately the same speed. It's not speeding up or slowing down, so that's what we mean by uniform circular motion. In the first part of this lecture on chapter 6, we talked about the kinematics of uniform circular motion. The difference now is we're going to be talking about the dynamics. So we're going to be dealing with forces and accelerations and so forth. So we're going to be using Newton's second law and apply it to uniform circular motion. So Newton's second law, as you know by now, is net force is equal to ma. What we're doing in this chapter is we're going to be talking about the net force in terms of a net centripetal force pointing towards the center of the circle, and the acceleration here is going to be a centripetal acceleration, which was introduced in part 1 of this lecture. So it's the same Newton's law, F equals ma, but it's being applied to something a little bit different here. Now we've got a centripetal force over here, and we've got centripetal acceleration here. The direction of the acceleration, remember, for centripetal acceleration, it literally means center seeking. So we will typically choose the center of the circle as our positive direction. So in this diagram here, where we have an object going around in a circle, there are several vectors shown. Each position here shows the velocity vector, which is pointing always off tangent, straight ahead from the direction it's moving. And then pointing towards the center of the circle, there are two forces. There will always be a net force pointing towards the center of the circle. This is required to make this object move in a circle. So in other words, anything that's going in a circle will have force pointing towards the center of the circle. It's usually one of the objects and challenges of the problems or questions that we're going to work on is trying to identify what is that force that's making this item move in a circle. The other vector shown here, of course, is the centripetal acceleration vector, and as we learned in the last part, that also points towards the center. So what we can do here is, with Newton's second law, is the centripetal acceleration, a sub c, remember, is equal to v squared over r. So we can rewrite Newton's second law like this. The net force pointing towards the center of the circle is equal to mv squared over r. Another form of it, which we'll probably not be using as much in this chapter, is where we replace a sub c with omega squared times r. So this is just an alternate way to express this equation. So again, one of the key concepts here for doing all these problems that we're going to encounter in this lecture is that whenever something is moving in a circle, there must be a centripetal force pointing towards the center of the circle. So one of our first goals will always be to identify the centripetal force. What is causing the centripetal force? Is it tension from a rope? Is it gravity? Is it friction? Is it a normal force? Or is it something completely different? So what we're going to do in this lecture is just go through and work through and solve a bunch of different problems showing a whole variety of applications of applying Newton's second law to circular motion. So let's get started. So here is our first example. We've got Dad puts his 20-kilogram child on a 5-kilogram cart attached to a 2-meter long rope. So here's Dad in the center here. He's got this rope here. By the way, this 2-meter long rope, obviously that's going to be the radius of our circle. And he's going to spin the cart around and around in the circle. So he's giving his child here a ride as the kid travels around and around in a circle like this. we're told that it takes 3 seconds for the cart to make a full circle. And we're going to ignore friction, probably reasonable since this cart is on wheels here, so there wouldn't be much friction involved for the cart here. So we're going to do 4 different things here. We're going to calculate the speed of the cart, calculate the angular speed of the cart, calculate the acceleration of the cart, and ultimately find the tension in the rope. So our first task is to identify the centripetal force that makes the cart go in a circle. Well, I think you can look at this picture and figure out pretty easily in this first example, what is the centripetal force? What's the cause or the source of this force that makes this cart go in a circle? So think about this, and then we'll go to the next slide. So the source of the centripetal force is going to be the tension in the rope here. So let's go ahead and just answer these questions. So the first question, part A, was to find the speed of the cart. So remember that for something going in a circle, the velocity is equal to the distance it travels divided by the time. So it's usually convenient to use the circumference of the circle as the distance. In other words, we're going to start with the cart right here. We're going to let the cart go all the way around the circle and come back to here. So it has now traveled 2 pi r distance. And we know r is 2 meters. We were given that. And the time it took to do this is the period of the rotation, and we were told it takes 3 seconds to go around once. So we have 2 pi times 2 divided by 3, which gives us a speed of 4.2 meters per second. Part B said, what is the angular speed or angular velocity of this cart? So remember, one of the equations is that velocity is equal to omega times r. So omega is equal to velocity divided by r. So we have 4.2 meters per second as our velocity from part A, divided by the radius of 2 meters, gives us 2.1 radians per second. Part C was calculate the centripetal acceleration of the cart. So there are 2 ways to do this. We can use centripetal acceleration is equal to v squared over r, and we could just plug in v as 4.2 and square it and divide it by r, which is was given as 2 meters. Or the other way to do it is use the equation centripetal acceleration is equal to omega squared times r. So we just figured out omega here, 2.1. We square that and multiply it by the radius, which is 2 meters, and we get an acceleration of 8.8 meters per second squared. So either method here will give us the same answer. Okay, for the final part, part D, it said calculate the tension in the rope. Well, so here's where we use dynamics now. We're going to use Newton's second law. Net force, all right, pointing towards the center of the circle, has to be equal to the mass of the cart times the centripetal acceleration of the cart. All right, and the center of the circle is going to be our positive direction. So this is showing a free body diagram, which may or may not help you, but this is showing the cart right here, and the center of the circle is over here. So the tension force is pointing towards the center of the circle. Now the cart also has weight down and normal force up, but those forces, of course, cancel each other because the cart is not moving in the vertical direction. And also, we really are only concerned with forces pointing towards the center of the circle here when we use Newton's second law for circular motion. So our net force is just the tension in the rope. That's the only thing making this cart go in a circle. So the tension is just equal to the mass of the cart. Remember, the cart and the child together weigh 25 or have a mass of 25 kilograms. And our centripetal acceleration is 8.8 right here. So 25 times 8.8 is 219 newtons. That is the rope's tension. So this next example is sort of a semi-conceptual type example. We're not going to actually use any numbers here, but this is a good one to apply circular dynamics of uniform circular motion to a situation where you might not really at first think about circular motion. So the situation is we have 3 cars that are driving at the same uniform speed along the road shown. So car A is driving on a level, flat road. Car B is going over a hill or a hump in the road here. And then car C is driving down inside of a dip in the road. Okay, so at first glance, you might not even consider this being circular motion, but it actually is. And one of the key things here is to recognize that any curved path of an object can be considered to be part of a circle. All right, so we can consider this curvature up here to be part of the arc of a large circle with a center somewhere down below. Likewise, this car here is driving on the inside of a circular path, right? This is part of a circle here, and the center of this circle would be, somewhere up above the car. So for each of these situations, we're going to compare the normal force to the weight of the car, and then how does your apparent weight compare in each case? And one thing to remind us here is that apparent weight is how much normal force we feel. In other words, how much we feel our body being pressed against a surface. So here's the solution. For the car in part A, it's driving along a horizontal path. So the weight of the car down is just equal to the normal force up, like we've seen, right? The car is not moving in the vertical direction at all. It's only moving horizontally. So there's no net force. These two forces balance. And in this case, then, the apparent weight, in other words, how heavy you feel inside the car, is just equal to your actual weight. You would feel the same as if you were just sitting on a chair at home. Now, let's look at case B here, which is a different story. Now our car is going over the top of this hump. So it's going along a circular path here. Notice that the center of this circle would be down below, somewhere down here probably. So we know that the centripetal acceleration of an object always points towards the center of a circle. So the net force must point in the same direction as the acceleration. So in other words, centripetal force always points towards the center of the circle as well as the centripetal acceleration. So we must have a net force that points down. All right, over here, there was no net force. Here, there is a net force. It has to be pointing down. That's what makes this car go in a circular motion. So how do we have that? Well, the weight of a car never changes. The weight is just mg, which does not vary. What does change is the normal force on the car. The amount of pressure or force between the road and the car is going to change depending on these three situations. So in order to get a net force pointing down, the normal force must be reduced here. It must be less than it is over here. And so if we add these two forces together, we get a little bit more force pointing down than up. So our net force is down. Now, what does this mean? Well, the apparent weight, what you feel inside the car, is less than your actual weight. You will feel somewhat lighter in the car. And think about taking this to the extreme. What would happen if you drove your car really fast over this hump? Well, you would catch air, right? You would go airborne. And at that point, this normal force actually drops to zero because you're not making contact with the road anymore. And when you have no normal force on you, you basically have no apparent weight. So you would feel weightless. And that's because you would be in free fall. You would actually be flying through the air, falling to the earth, and you would be experiencing no apparent weight. Okay, so now let's look at situation in part C. In this part, the car is going down inside the dip. Now for this circular path, the center of the circle is somewhere up above the car. So that means its acceleration always points towards the center of the circle. So the acceleration is going to point upwards, not downwards like here. It's sort of the opposite situation. Therefore, we must have a net force pointing towards the center of the circle. That's what makes this car go in a circle. So what are the forces on the car? Well, again, we have the car's weight, which is mg. That doesn't change. Therefore, the normal force on the car must be what is causing this force pointing up towards the center. The normal force has grown here. It's larger than the weight. So when we add these two vectors together, we get a net force pointing upwards. This is the centripetal force that's causing this car to go in a circle. And the origin of this force is, of course, this larger normal force here. So what's happening here is your apparent weight, remember, which is equal to your normal force, is larger than your actual weight. So you'll feel really heavy down here at the bottom of this dip, because basically you're being pressed against the bottom of the car and the car is pressing against you, giving you the sensation of a heavier weight. One of the neatest things about problems involving uniform circular motion is the fact that you can go upside down, for example, in a car like this, without falling off the track. You've perhaps done this in a roller coaster, where the roller coaster goes around the loop and you don't fall out of the roller coaster, and the roller coaster doesn't fall off the track. So why is this? Well, we're going to look at this a little more carefully in this problem. So the question is, what is the minimum speed the roller coaster must have at the top of the loop so it doesn't fall off? So in order for you to be safely touching and in contact with the track, there needs to be a normal force present. So the normal force is due to contact between the car, the roller coaster car, or this car here, and the track. So things become dangerous when the normal force disappears. That means the car is going to fall off the track. So we want to make sure that we still have contact with the track. In other words, we don't want the normal force to become zero or less. So let's set up our problem here with Newton's second law. We have net force in the centripetal center of seeking direction is equal to m times the centripetal acceleration, F equals ma. So again, we're going to choose the center of the circle as our positive direction. So let's take a look at, we'll look at this daredevil here in his car. So he's riding around in a circle here in this loop. So let's draw a free body diagram of this car. Well, the car, of course, has weight, which is equal to mg, so that points down as always. Now, the normal force also points down, because think about it, the car is upside down and it's touching basically, the ceiling here, right? The top of the track there. So the track is pushing on the car in a downward direction. So this is, the first time we've seen a normal force that actually points down, and that's just because the object is upside down. So our Newton's second law then, we have to add up the forces that point towards the center of the circle. So you can see they both point towards the center. So I've got mg plus the normal force, and that's equal to the mass of the car times the centripetal acceleration, which remember is v squared over r. Now what we're going to do here is we want to find out what this speed is when the car loses contact, just when the car starts to fall, because that's going to be our minimum speed. Anything greater than that speed will ensure that we still remain in contact with the track. So what we can do to find this minimum speed is set the normal force here to 0. So we're just going to cancel it off here. So we've got mg equals m v squared over r. Now notice on both sides of the equation there is an m. So we can cancel those m's, and we see something very interesting here. We see that g, which is the acceleration due to gravity, is equal to v squared over r. But remember, v squared over r is the definition of centripetal acceleration. So our centripetal acceleration at the minimum speed required is equal to that of gravity, 9.8 meters per second squared. And again, that sort of makes sense, because if we weren't going if we weren't going quite fast enough, we would actually start to fall, and we would be accelerating with the acceleration due to gravity, which is g, or 9.8. So anyway, let's go ahead and solve this equation for v. So we'll multiply both sides by r, so we get v squared equals g times r, and we take the square root. So the minimum speed required for a safe ride is the square root of g, which is 9.8, times the radius of the loop. So in this picture here, the radius is this distance here. For our roller coaster here, the radius would be something like here up to the top. Okay, so when an engineer designs a roller coaster, they have to make sure, obviously, that this roller coaster has enough speed to make it safely around the loop without the cars falling off or without people falling out of the cars. And this is done by ensuring that V is greater than the square root of G times R. Next, I'll show you a video demo that is kind of fun to do. So in this demonstration, I'm going to take this basket and put some tennis balls in there. Obviously, if I turn the basket upside down, we can see the tennis balls fall out. But one thing I can do now is let's try spinning the basket over my head upside down. And notice the balls stay in the basket. Now let's make it a little more interesting. I've got a glass of water here. You can see it's about half full of water. So I'm going to put the water glass in the basket. And let's do the same experiment here. And here's our glass of water. Still in there, and not a drop came out in the basket. Cheers. Here's another problem involving dynamics of uniform circular motion. Does the coin slip? So a coin sits 20 centimeters from the center of a turntable rotating at 3 radians per second. So here's the picture. So a turntable, you can think of it like the old-fashioned record player, right? This disc here is spinning around, and we've got a coin sitting out here, and the distance from the coin to the center is given as 20 centimeters. Furthermore, we're told that the coefficient of static friction for the coin is 0.3. And the question is, will the coin stay on or slip off? So what happens here is if you set something like a coin on a rotating platform like this and turn it very slowly, it's easy to see that this coin is not going to slip. It's just going to stay there. But if you start turning this thing faster and faster, you'll get to a certain speed when all of a sudden the coin slips off. And that's because basically the static friction was not sufficient to keep the coin from slipping. So as is always the case with these problems, we have to identify what is the force that's making this coin go in a circle. There must be a force pointing in toward the center. So the coin, of course, has weight going down, mg, and it has a normal force pointing up, but those two cancel each other because the coin is not moving vertically at all. There must be a force that is pointing towards the center of the circle, and the force is static friction. Okay, the static friction is basically preventing this coin from slipping off the edge of this turntable. So that static friction force is pointing towards the center of the circle. It is our centripetal force. So we need to see if the maximum static friction is sufficient to rotate the coin at 3 radians per second. All right, that was given to us up here, the speed. So let's go ahead and write Newton's second law. The centripetal force, F sub c, is equal to ma. All right, remember we only have one force here, which is that static friction force. And we're going to replace centripetal acceleration with omega squared times r. Also, again, we're choosing the center of the circle as the positive direction, as we always do. So this force here pointing towards the center is a positive force. So the maximum possible static friction, remember from chapter 5, the max static friction is given by mu times the normal force, mu sub s, right? This is the static friction coefficient, which, by the way, is given to us as 0.3. And the normal force, remember, is just equal to the weight, mg, because these forces balance. So for no slip, we would need the condition that the centripetal force is less than or equal to the maximum static friction force. So we need this expression here, m omega squared times r, has to be less than mu times mg. Notice m on both sides, we can cancel that. And so we have omega squared r has to be less than mu times g. So let's plug in our numbers. Omega is 3, r is 0.2, mu is 0.3, and g is 9.8. So on the left side, this turns out to be 1.8. On the right side, this turns out to be 2.94. So this condition is true. 1.8 is less than 2.94, so therefore there is no slippage. Okay, the coin does not slip off the turntable.
I'll bet most of you don't know what this is, or at least have never seen one before. So back when I was a kid, this was the way that we listened to music. This is an old-fashioned record player. So what I'm going to do here is just like in the problem we just analyzed, I'm going to take this coin here and set it on the turntable. And right now it's spinning at 33 1/3 RPMs. So this was the speed that long play albums, vinyl albums would play at, or LP albums. And as you can see, the coin stays on the turntable. So in other words, the static friction is sufficient to keep it from slipping off. So let's now ramp up the speed. The next speed setting on here is 45. And maybe you've heard of 45s. 45s were typically single track songs instead of a whole album. So you can see now it's spinning faster, but our coin is still remaining on the turntable. Well, if you really go back far, this is even before my time, if you can believe it, your grandparents used to listen to records at a speed of 78. And the old albums were called 78s. And some of those were not even vinyl. They were actually made of material that would break if you dropped them. So let's see what happens if we go up to 78 revolutions per minute. And we can see now that our coin slips off. We've exceeded the maximum static friction force, and the coin slips off the turntable.
Our next example is interestingly similar to the coin on the turntable. In this example, how fast can you make that turn? So most neighborhood intersections have a right turn radius of about 10 meters as shown. So what that means is if you're driving your car along here and you're going to make a left turn, a right turn, you're basically following the arc of a circle shown here, which is approximately 10 meters in diameter. So what this means is that when you make a turn in your car, you're undergoing uniform circular motion. Okay, and so that's how we can apply that to this problem. So the question is, how fast can you drive your car to make the turn without skidding? So the first task is to identify the centripetal force that makes the car go in a circle. So remember, one of the key things here is whenever something is going in a circular path, we know there has to be a force involved that makes the object follow that circular path. So your first task here is to think about, in this problem, what is it that makes the car go in a circular path? What type of force is it? Well, the answer to that question is, again, static friction. And this is kind of interesting because the car is obviously moving, right? It's not stationary. So you might think, well, wouldn't it be kinetic friction or rolling friction or something like that? Well, the answer is no, because here's why. The car is moving forward. That is true. But the car is, the static friction force is preventing the car from going in a straight path. It's allowing the car to curve and go on along a circular path like this. So the static friction is pushing towards the center of the circle over here. All right, the static friction on the wheels is pushing this way. That's what keeps the wheels from skidding. If you were to go too fast around a turn, your wheels would actually skid. And then, it's not static friction. Then it would be kinetic friction. Okay, but that's kind of the tricky part of this problem is being able to understand that it's static friction that allows you to make a turn. And it doesn't have to be a car. When you walk or run, if you walk and change directions, turn right or left, it's static friction between your feet and the ground that allows you to turn, not kinetic friction. Okay, so the force that's pushing towards the center of the circle causing the car to turn is static friction. So in the y direction, here's a free body diagram. This is looking at the car from behind. So here's the car. We've got weight down, normal force up. Well, the car is not moving in the vertical direction, right? It's on a horizontal road. So these two forces have to balance each other out. We have equilibrium in the vertical plane. So the normal force on the car is just equal to its weight, which is mg. So that's what I've shown here. In the horizontal direction, this is where we're going to apply Newton's second law for circular motion. So the forces in the x direction pointing towards the center of the circle has to be equal to m times the centripetal acceleration. All right, so we have the max static friction here is equal to m times v squared over r. Remember, v squared over r is the centripetal acceleration. And the maximum static friction, just like the last problem, is mu s times n, and that's equal to m v squared over r. Normal force here, we're going to substitute mg for the normal force, and now we can cancel out these two m's here. We can divide by m, so we get mu times g equals v squared over r. And again, let's solve for v. V squared equals r mu g. So v is the square root of r mu g, and we can plug in our numbers. Remember, the turn radius was 10 meters. The coefficient for static friction of rubber wheels on cement or concrete surface, all right, we're assuming, this is a car tire on a road. If you look it up in the table back in chapter 5, the coefficient is 1. It's 1.0. And then, of course, g is 9.8. So multiplying these numbers together and taking the square root, we get 9.9 meters per second. I converted that, and that's the same as 22 miles per hour. So this is an estimate of how fast you can safely make a turn in an automobile without slipping, all right, without losing control of your car. And obviously, this answer would change if the road is wet. So during rain, for example, one reason you need to slow down is the coefficient of friction is certainly going to be reduced because of the slippery road, and therefore this speed is going to be considerably less. All right, here's an example where we have a ball on a string that is actually going around in a vertical circle. So again, the ball on the string, it's traveling around and around like this. But in this case, the circle is not parallel to the ground. This part down here is closer to the ground, and this part here is up towards the sky, right? So this is a vertical circle here. We're told the mass of the ball is 0.1 kilograms, the radius is 1 meter, and the speed is 5 meters per second. We're asked to find the tension in the string at each of the 4 positions shown. So we've got, this position here at the bottom, at the top, and then the 2 sides. So again, as always, let's choose the center of the circle as our positive direction. So anything that points inward towards the center, we're going to call that a positive force. So at the bottom, let's look at this picture here. So we draw the free body diagram. So this is good practice to see all these different situations. So what's acting on our ball down here? Well, we have weight, mg, pointing down, and we have the tension of the string pointing up. Okay, we'll call that T1. So we can write Newton's second law, the net force towards the center of the circle is equal to m times a centripetal, right? This is a centripetal acceleration. So based on our picture here, this force points towards the center of the circle. So T1 is positive, mg is negative because it points in the opposite direction. So we have T1 minus mg equals the mass of the ball times v squared over r. Remember, v squared over r is, of course, the centripetal acceleration. So what we're going to do here is just solve for T1. So it's just a few steps of algebra. So when we do that, we get 3.48 newtons. All right. Now let's compare this for the position. Let's redo our problem for the top position up here. So again, we're going to draw a free body diagram. Well, weight always points down, so mg points down. And of course, the tension of the string is also pointing down here, right? Because the tension always pulls towards the center of the circle. So if we look at this picture, we've got two forces here. We've got the tension 3 and we've got mg, both pointing towards the center of the circle. Remember, these are both positive forces because towards the center of the circle is our positive direction. So this time we add these two forces, T3 plus mg equals mv squared over r. And when we solve for T3, we get 1.52 newtons. All right, so look at the difference here. At the bottom of the circle, the tension is 3.48. At the top of the circle, the tension is only 1.52. Therefore, if we draw this sort of to scale, the tension here, we're going to draw this as a long vector. The string is tighter down here than it is up here. The reason for this is the ball is traveling at the same speed. So the centripetal acceleration is the same everywhere. Well, down at the bottom, the tension and gravity are working against each other. So the tension has to be much larger in order to get the same net force pointing towards the center. Up here, however, gravity or weight is working with tension. It's helping it. Therefore, the tension doesn't have to be as strong to get the same centripetal acceleration. Now, the last part of the problem is what about here on the sides? Well, notice in either side, we have tension pointing towards the center, and we have weight down. So in this case, the weight does not act at all towards the center of the circle. So it's not going to be contributing to the centripetal force. Same over here, right? The weight is pointing down, but the center of the circle is, horizontal. So for the side here, the only force present is the tension T2, and we set that equal to ma, or mv squared over r, and plugging in the numbers, we get a number in between these two numbers. We get a tension of 2.5 newtons. Here's our next example, which is sort of a surprising use of uniform circular motion, and that is walking. We don't usually consider when we're walking just down the street on a flat horizontal surface, we don't really think about this being circular motion, but we can model the motion of our hips and our leg as circular motion, which brings up an interesting way to estimate the maximum walking speed. The idea here is that if we walk too fast, we'll actually lift off the ground, and then by definition, we are running. The definition of walking is both feet have to be on the ground at some time, or at least one foot has to be touching the ground. We can't have both feet up in the air, or else that's by definition running. Now, how is this circular motion? Well, if we look at the photo here, we can see that the woman's leg here represents the radius of a circle. The center of the circle is right down here where her foot is planted. So as she strides forward and takes a step, her hips here are actually undergoing uniform circular motion because her leg is relatively straight, so that keeps a constant radius, and therefore her hips are actually tracing out an arc of a circle here. So during this time here, this is where we're going to model this problem and figure out how fast you can walk without leaving the ground here. So if we look at a free body diagram, we've got weight down and we've got the normal force of the ground pointing up on our foot there. Now, in order for there to be circular motion here, we need a net force pointing down, okay? So we're going to, let's go ahead and look at this in the next slide. So let's go ahead and apply Newton's second law to this walking situation here. Again, we're going to choose the center of the circle as the positive direction. So remember, this is our free body diagram. The center of the circle, remember, was down. It was where her foot was placed against the ground. So W, the weight, that'll be our positive force. And the normal force, since it's pointing up away from the center of the circle, that will be negative. So our net force towards the center of the circle is weight minus the normal force, and that's equal to m times the centripetal acceleration, which is v squared over r. Okay, so weight is always equal to mg, all right? But the normal force here is not equal to mg necessarily. because she's in, uniform circular motion here, and so the normal force is probably going to be less than her weight. So let's just leave it as n for now. So what we're going to do is solve this for v squared. So we can multiply both sides of the equation by r and divide by m, and we get an expression for v squared, and then we can take the square root, and we get v is equal to square root of r times mg minus n over m. Now, what do we do with this result? Well, we see in this equation that when the normal force becomes smaller, all right, we get a larger walking speed. Okay, so because we're subtracting it here. So if we take away a smaller number here, that's going to make this velocity or speed of walking larger. So we want to walk the fastest possible. We need n, the normal force, to be as small as possible. Okay, but the smallest normal force allowed, of course, is 0. At that point, the walker has lifted off the ground. So once n disappears here, then we're at the transition between walking and running. So we basically want to solve for this walking speed at that transition point. So to do that, we just set n equal to 0. So we get the speed of walking is root r mg over m. Notice the m's cancel, and we get the square root of r times g. So let's put in some typical numbers here. So for an average height person, their leg length from ground to hip joint would be about 0.7 meters. And we multiply that by g, which is 9.8, and take the square root, and we get 2.6 meters per second, which is about 6 miles per hour. And that is a reasonable estimate for how fast you can walk before you actually start running. And the other interesting thing here is that obviously the longer your leg is, the faster in theory you'll be able to walk before you start to run, because that will make this number inside the parentheses larger. So here's sort of another semi-conceptual problem that just illustrates some of the characteristics of uniform circular motion and dynamics. With the Ferris wheel here, we've got a daredevil that's standing on top of the Ferris wheel chair. I'm not sure why he's doing this, but as it rotates around at a constant speed. So here he is up here on the chair, and this thing is, of course, going to go around in a circle like this. So we're asked to sketch the forces on the daredevil at the 4 positions shown. The first part here is to sketch the forces. So let's start, we can start down here at the bottom, for example. So the daredevil has weight, always mg, pointing down, and there is a normal force pointing up. Okay, now those are the only 2 forces on the daredevil. And the same thing up here in the top position, weight is down and normal force is up again. The interesting thing happens here over on the sides. Weight is always down, mg, and the normal force is going to be pointing up again because that's pushing on his feet. But notice these 2 forces, normal force and weight, are pointing in the vertical direction. There's nothing pointing towards the center of the circle. We know that if he's going to be going in a circle, there has to be a force pointing towards the center of the circle. So what is that force? Well, think about this. If this were really slippery up on top here, he would slip right off of this thing. So what's keeping him on the top of this chair here is static friction, okay? And that's going to be pointing towards the center. Likewise, over here, static friction is pointing towards the center, towards the right. So which position is the normal force the largest? Well, this is going to be at the bottom position. And again, this kind of goes along with that similar problem we did a couple slides back with the ball on the string that was going in a vertical circle like this as well. Remember, we need a net force pointing towards the center of the circle. So the only 2 forces available here are normal force and mg. All right. So the normal force must be larger than mg here in order for us to have a net force pointing up. So here is going to be the largest normal force. And likewise here is going to be the smallest normal force, because in this case, again, we need mg pointing down and normal force up, and these two forces have to add together again to give us the total force pointing towards the center. The other way to think of this is he will feel the heaviest down here where the normal force is greater, and at the top he will feel the lightest. In fact, if this Ferris wheel is going too fast, the normal force may disappear, meaning he's just caught air. He's gone airborne and he's not touching the chair anymore. Okay, and then we answered basically what causes the centripetal force at the 9 o'clock and 3 o'clock position, and that is the static friction force. There are so many different types of applications and examples of uniform circular motion. That's what kind of makes it interesting. So here's another one, which is a little bit different. This is the classic carnival ride where the kids are inside this giant spinning drum. And what happens here is after it starts spinning fast enough, the floor drops out, and basically the people are stuck to the walls, right? They're not slipping down because of gravity. They're literally stuck to the wall, and it's kind of an interesting effect here. So this carnival ride, the wheel has a radius of 5 meters. We're going to assume a coefficient of static friction of 0.3. What is the minimum angular velocity of the wheel needed to prevent the riders from slipping down? So the way this works, the reason, notice these kids are just sitting. They look like Spider-Man, right? They're sitting on the wall of this ride. How is that possible? Well, what's happening here is this is looking at it from the side. The kid has a weight going down of mg. The normal force here is, remember, that's the side of this wall here pushing on the child. So the normal force always points normal to the surface. So it's going to point in towards the center of the circle. In fact, this is the centripetal force here. What prevents the kid from slipping down and falling is this. It's static friction, okay? So in the vertical direction, we have the maximum static friction, that's this force here, is equal to mu s times n. So, and we want this static friction to be at least equal to mg to prevent the child from slipping down. So we can replace the maximum static friction with mg. So we have mg is equal to mu times n. We can solve for n, which is equal to mg over mu. So we're going to use this. This is an equation or expression for the normal force here, which is the wall pushing on the child. We'll use that over here. Let's now go to the horizontal direction. So here is where we use Newton's second law for centripetal forces. So the centripetal force is equal to m times the centripetal acceleration. So the centripetal force, again, looking at this picture, the only force pushing this child towards the center of the circle is the normal force, all right? The force of the wall pushing on the child. That's what causes these kids to go in a circle. So the normal force is equal to m. Instead of using v squared over r, let's use the other form, omega squared times r for our centripetal acceleration. And we can replace n with mg over mu, which is done here. And the next step, we can divide by m to cancel out the m's. And finally, we can solve for omega. Omega is root g over mu times r. And we can plug in the numbers. G is 9.8. We were told the static friction coefficient is 0.3, and the radius of the ride is 5 meters. So this gives us an angular velocity of 2.55 radians per second. So as long as this thing is turning at more than 2.55 radians per second, the riders will remain stuck on the wall here. Pretty nifty. And notice our mass is canceled. Let's see, where was it? Right here. We had m over here and m here. They both cancel out. So this speed works for any size person, right? A small child or a big, large man. It would be the same speed for anybody. Here's a little more challenging problem. This one, I'm not going to work through the whole thing because this video is getting kind of lengthy now. However, I will mention this is a homework extra credit problem that you may be interested in doing if you're up for the challenge. This is a demonstration of what's called a conical pendulum. And a conical pendulum, from the top, it looks, similar to what we did before with the ball just twirling around on a string. But if we look at it from the side, we see that the ball is actually coming down at an angle. All right, so the length of the string is L, but notice the ball is actually traveling around in this blue circular plane here, and the radius of this circle is not L. It's not the length of the string. Because of this angle, the radius of the circle of motion is shown here as R. So we can do some trigonometry to figure out the true radius here. Notice it's going to be L times the cosine of theta. And so in this problem, we were asked to find the angle of the string in terms of the period and the length of the string. The solution is shown here. And again, this is a somewhat challenging problem, more than something I would expect you to be able to do on a quiz or an exam. So I'm not going to go through this one in detail, but if you're interested in how it works and also how to do the extra credit problem, you can refer to this slide here, which shows the complete answer with all the steps. So one thing you've probably heard before is this idea of a centrifugal force, not centripetal force, but centrifugal force. So far, all we've been discussing is centripetal force, which always points to the center of the circle. But what about this so-called force or feeling, right, that we sense that pushes us outward away from the center of the circle? So what I mean is this, and you've no doubt experienced this many times. Let's say you're driving your car around a sharp turn like this. Well, you'll notice that everything in the car, including the drivers and, if you had a cup of coffee sitting up on the dashboard or whatever, everything seems to be pushed out to the outside of the circle. Your coffee cup would slide to the outside of the circle, right? The inside of the circle is over here, the center of the circle. And we've been talking about centripetal forces pointing towards the center, but here it seems like something is pushing these passengers and the driver over here to the left. And the same thing, again, if you had a coffee cup sitting on this car, it would slide outward, right? So is there some sort of force that actually points to the outside of the circle? Well, this is what is sometimes called a centrifugal force, but it's not a real force. In fact, it's called a pseudo force in physics. Centrifugal force does not actually exist. Centripetal force is real. All right, so how do we reconcile this? Because again, if we think of this carnival ride here, it looks like these kids are being pressed against the wall here, like there's some force pushing them to the outside, but there's not. Interestingly, the only force on these people here is pointing towards the center of the circle, and the same goes here. So let's see if we can explain this. The best explanation for this kind of paradox here is to think about what would happen if you were in your car and you were driving to make this left turn here. What would happen if you didn't have a seatbelt on, and let's say you were sitting on top of your car, all right, not inside of your car? What would happen? Well, your car would make the turn and you would just keep going in a straight line. You would literally just slip and slide right off the car, and your motion would just continue going in a straight line, which was the direction of your travel before the car turned away from you. So what actually happens when you're inside the car is the car, like the side of the car here, and the seat belt around you is actually pushing you this way to the left. It's pushing you towards the center of the circle. This is the centripetal force, which is a real force. There is no force, there is no centrifugal force that pushed this person to the outside. It's just a tendency for them to go in a straight line in the absence of a centripetal force. So your natural tendency to move in a straight line is being resisted by the walls and seat of the car, which push you inwards towards the center. There is no such thing as a force pushing you outwards. Finally, here is our last slide of this rather long lecture. Thank you for your patience here, but there were just So many different types of problems that we had to work through. So here's a little conceptual quiz for you to take that will be similar to something you might see on an exam or quiz in class. So here's our guy again, and he's twirling this ball around over his head in a circle like this. We're looking down at this from up on the ceiling. And all of a sudden, when the ball gets right here, the string snaps. All right, he was twirling it too fast. Too much tension in the string, and the string snaps. So the question is, which path does the ball take? And your choices are the ball goes straight out, all right, from the position that it was in here from the center. That's part A. Part B is it kind of goes out, but it remains curving like this. Part C, it sort of goes at an angle, but in a straight line. Answer D is it goes in a straight line, but in this direction, tangent to the circle. And part E is it follows a curved path after it leaves a circle like this. Now remember, we're looking at this from above. We're looking at this from a bird's eye view. So think about this a little bit here. Maybe pause the video and think about which one of these answers you think is correct. Well, I'll tell you which answer is not correct, and that is answer A. A lot of people, especially before they would watch this lecture, would choose answer A. And the reason for the thinking there is we know that there's tension in this string. So the string was pulling on the ball to the right. So so that means the ball must have been pulling on the string to the left. So people sometimes falsely associate this with a force on the ball pointing to the outside of the circle. And remember, this is this sort of false notion of a centrifugal force, an outward force. But there is no such thing. There is no such force. So what we learned in the last few slides is that if this string were to break, the ball would continue on its forward path in a straight line tangent to the circle. So the correct answer here is answer D. I hope you enjoyed this lecture. We'll see you next time.